Um, you can do this one. This one is pretty chill vibes. So the steps, I always like to kind of put things in steps in my mind from how they make sense to me. Basically what you do is you're given a function. It's either in terms of y or x, and you're given the bounds. Say x is between this and that. And then what you do is you just take the derivative in respect to what that equation is in respect to, and then square that, and then plug that into this. Arc length equals the square root of 1 plus your derivative of the given equation squared. And so you plug that in an integral with the bounds that you were given, like x is between this and this. That's literally the section. So pretty cool. Here, let's do a problem. Section 8.1 in Stewart, arc length. And if we're given something like x equals sine of y, 0 and pi over 2. Okay, this is what's given. And if it's saying, hey dude, I want you to set up an integral for the length of the curve. And so what this pretty much looks like is, if we're given this function of sine at some point between 0 and pi over 2, they want you to find the arc length of this, essentially. So that's kind of what we're looking for. Is we're looking for that curve. What is that arc length? And so that's, thankfully, someone miraculously, it's pretty impeccable how people figure this stuff out. But we figured out how to put that into an equation, which is pretty cool. So let's start the problem here. Like I was saying earlier, we take the derivative of x in respect to y, then we would get cosine of y, right? Pretty cool. Pretty cool stuff. So now we're going to square this, and then we can get cosine squared y. Okay? What's our equation? L equals the integral. Did I write that down? Okay. I don't know what's going on. The length of the thing is from 0 to pi over 2 of 1 plus this, right? Miraculous. You did it. All right. So this is how you solve that problem. Pretty cool. All right. Cool. How does it look like when we actually need to do crap? Well, let's do crap. Let's see what happens when we do crap. So, a problem like 11 in chapter 8.1 exercises, where we have y equals 2 over 3, 1 plus x squared, 3 over 2. Hey, knowing derivative rules, that's going to give you a 1. That's kind of cool. What are our bounds here? 0 and 1. That is spectacular. Okay. Again, we're going to have this function, you know, and then eventually this function is going to have some curve between 0 and 1. What is going on here? What am I doing? Between, 0 and 1, and then we need to find this. Oh. Okay? Again, not too shabby. There's a process here. Very intuitive. So we start with blue. Take the derivative of y in respect to x, right? And then doing that, this 3 over 2 times 2 over 3 becomes 1, okay? And then take the derivative of the inside, so 2x. Take the derivative of the inside, multiply it to the inside function, and then take that minus 1. So this becomes 1/2. Now, now I don't even do that a lot of the time. I actually write out my chain rule. So if you guys want to see that, it pretty much just looks like this. If our big function is the whole thing, our inside function is 1 plus x squared. So our f of u is 2/3 times u to the power of 3 over 2. Now, if you guys remember chain rule, it looks like this. This is 2x. The derivative of the outer function becomes u to the power of 1/2. Okay, and then this is your formula, okay, which ends up being u of g of x. So 1 plus x squared to the power of 1/2, right? And then times 2x times the derivative of g of x. That's where that comes from, okay? So, chain rule. Calculus 1. Calculus 1 things. We've done this before. I've played these games before. You guys see that new season of Squid Games yet? I haven't seen it. I've been doing math. All right. So, this is funky, isn't it? Well, because we square each term, this will become 4x squared, and this just goes away. This square root. So that's not too bad. Okay? Now, what is our equation? L equals 1 plus dy over dx squared, right? So, let's do it. If we have that, it's going to look like this. Okay. So, oh, don't forget your bounds. All right. Now, this we can factor out. 1 plus 4x squared plus 4x to the power of 4. Now, this we can work with. This we can freaking work with. Because this can turn into something we can factor out. 2x plus 1 this becomes 4 is the fourth. All right. 4 4x to the fourth plus 4x squared plus 1. See where I got that? So this becomes 2x squared plus 1, 2x squared plus 1 because we factor it out. Holy guacamole, guys. What am I forgetting here? Forget my dx. Do not disrespect the integral. You gotta show the integral some respect. Alright. So we have this. Now what we can do is say, wait a minute, these are squared. So this is just going to be like this. Look how spectacular that is, because then this becomes right? Check that out. Now we can integrate that. So let's do that. Let's integrate it. So this becomes 2x squared integrated becomes 2 over 3x to the power of 3. Okay? And then that's just integrating it from 0 to 1. And then this becomes that. And so now we can say, with the fundamental theorem of calculus, that 2 over 3 x cubed plus x from 0 to 1. Sorry, so that's going to look like this. Okay, 2 over 3 plus 1 is 5 over 3. Boom. That's how you do these problems. They're all the same. The trig ones are a little bit more annoying because it's just, they just are, because they're trig. So you're going to have to know some identities for those, but maybe we'll pop one of those on here. That's the problems, though. Yeah.